Okay, so let us start from where we left off in the group theory exercises. It's been a while. So in this one, we are asked to find the number of subgroups of Dn of order n. We know that the dihedral group Dn itself has order 2n. So as a solution, I will simply write the number, and in fact the entire solution is available at the end of the text in the answers section, where you have answers to some selected exercises. So the solution is just this: when n is odd, Dn has no subgroup of order n, and when n is even, Dn has exactly one subgroup of order n. So you go to the answers and you will see why. Next, 82. So the 82nd one is this: let G be the set of all polynomials of this form: ax square plus bx plus c with coefficients from this set consisting of the integers 0, 1 and 2. That means this a, b and c, these are coming from this set, and G is the set of all such polynomials. We can make G a group under addition by adding the polynomials in the usual way. But we have to keep in mind, except that we use modulo 3 to combine the coefficients. That means when we add two such polynomials, clearly the usual way of adding two polynomials is to add the like coefficients, and in that addition we are using modulo 3 version of the addition, ordinary addition. That is, now our addition is addition modulo 3 when we add the coefficients. With this operation, prove that G is a group of order 27 that is not cyclic. So there are 3 parts to the solution. We have to first prove that it's a group, and then its order is 27, and then we have to also somehow make sure that it is not cyclic. Showing that it's a group is very easy. So okay, instead of again writing what G is, we start writing the actual solution. Let a1x square plus b1x plus c1 and a2x square plus b2x plus c2 belong to G. That means this a1, b1, c1, a2, b2, c2, they are all coming from this set. Then adding them, we get this. Since and we are using the operation addition modulo 3 or we can just simply write till this much, addition modulo 3 hence the above sum of the two polynomials is in G. This sum is in G. That means G is closed under this operation. The sum is clearly associative because addition modulo 3 is an associative operation. This we already know, and that is because when we add two such polynomials, ultimately things come down to adding the like coefficients. So if you add three such polynomials in those two different manners, in these two ways, say these are two such polynomials which we add, and then with the sum we add another such polynomial. If you form this sum, what you get is the same as this one. For example, if your f is this, g is this, and suppose in H the coefficients are a3, b3 and c3, then in this sum, in this first sum, the coefficient of x square will look like this: a1 plus a2 plus a3, and the coefficient of x square in this second sum will look like this. And we should remember the fact that this sum is not ordinary sum, it is addition modulo 3, and these two things are equal because addition modulo 3 itself is associative. That's what we are saying here. So you can see that just like that, the coefficients of x and also the constant terms on of both these sums will be equal, and so the sums themselves are equal, and that's how our original sum is associative. The element 0x square plus 0x plus 0 belonging to G acts as an identity, obviously. Also, for ax square plus bx plus c belonging to G, there exist elements a prime B prime and C prime belonging to this set such that A plus A prime is 0, B plus B prime is 0 and C plus C prime is 0. If we wanted, we could have written in place of A prime minus A, but just to show that these are not ordinary negatives but additive inverses with respect to the operation addition modulo 3, I have decided to write these primes A prime, B prime and C prime, and you already know that this is true. For example, you see, whatever this A, B and C are, after all they are coming from this set. So if for example your A is 0, then A prime is also 0. So that 0 plus 0 is 0. If your A is 1, then A prime is 2. 1 plus 2 is 3 and modulo 3, that is 0. Just like that, if your A is 2, then A prime is 1. So additive inverses for these coefficients exist under addition modulo 3. So those additive inverses are A prime, B prime and C prime for these coefficients respectively. Then plus C prime is clearly equal to this, and we get the same thing if we change the order. Don't forget to show both the things when you are showing that a system is a group, because unlike this case, in some cases the operation may not be commutative. In this case it is. So there is really no need to write both the things here, but still I am writing. Okay, hence G is a group under the above operation plus. Okay, so that is the first part of the solution. Now still we have to show that G has 27 elements and G is not cyclic. Okay, so next we do that. Note that if ax square plus bx plus c belongs to G, then each of these coefficients has three choices, that is each one, say A, it can either be 0 or 1 or 2 simultaneously and independent of A being A taking some particular value. B can also be either 0 or 1 or 2, and independent of these two things, C can also be either 0 or 1 or 2. So in total we will get 27, 3 times 3 times 3, 27 such polynomials. But then another question will arise, whether all those 27 polynomials are distinct. They will be, because two polynomials are considered to be equal if and only if their corresponding coefficients are equal. So we write accordingly. There are, in fact, let's show why we get 27. 27 such polynomials. In G, since two polynomials are equal, if and only if their corresponding coefficients are equal, the 27 polynomials above are all distinct. So we get, of course, 27 symbols, and then then we also get the fact that those symbols actually represent distinct elements of G. So the order of G is equal to 27. Okay, this is not always the case. Sometimes it happens that two symbols that look different actually are the same thing. We will see these things when we what we will see. I think we can already give one example. If you here itself, if you think of the relation congruence modulo 3, for example, on the set of integers, we already know that congruence modulo 3 is an equivalence relation, and say we have two integers a and b. We say that a is congruent to b modulo 3 when 3 divides the difference a minus b. One can prove that this is an equivalence relation, and there are 3 distinct equivalence classes, and only 3 of them, which are, one of them is 0, the other is 1, and this one is 2. The class 0 consists of those integers that leave remainder 0 when divided by 3. Here we have those integers in class 1 which leave remainder 1 when divided by 3, and here we have those integers that leave remainder 2 when divided by 3. And they give us all the integers. They are mutually disjoint, non-empty, and their union is the set of integers. That is, they form a partition of the set of integers. What you ordinarily have when you have an equivalence relation. Now, instead of writing like this, one can also write, for example, 3, because just like 0 is a representative element of this class, the integer 3, or in fact any multiple of 3, is also a representative of the class. In other words, if you see what this is by definition is the set of those integers that are congruent to 0 modulo 3, and this by definition is the set of those integers that are congruent to 3 modulo 3, and these two sets turn out to be the same. So that is why, although these two symbols look different, actually they are the same thing in the collection of congruence classes modulo 3. That is not the case here for these polynomials. Whenever they look different, because these a, b, c are different, they actually are different elements in the group, and that comes from the fact that two polynomials are equal if and only if they actually look equal, that is, the corresponding coefficients are the same. Okay, so we have got the second part also, that G has 27 elements. Now finally we have to somehow conclude that G is not a cyclic group. You see, because G has 27 elements, for it to be a cyclic group, there should be one generator whose order should be equal to 27. However, you can almost easily see that the order of an element cannot exceed 3 for any element in G. We have, so because our binary operation is addition, so this integral power is actually this element, that is the sum of this element with itself, taking 3 of them, 3 copies of this. We have, okay, in fact why did I even write that up? So we would be adding 3 such polynomials, so their corresponding coefficients would be added. After everything is done, we will have a polynomial that looks like this. Where this 3a means a plus a plus a, and that plus of course is addition modulo 3, and because of that this is 0, this is also 0, this is also 0. So the third power, I should say in general, the third power of this element ax square plus bx plus c equals the identity. So if, for example, if you are denoting this element by say fx, then what we have done here can also be written in this form. So the third power of fx is the identity of the group. So that means the order of fx is less than or equal to 3. We can't say that it is equal to 3 because we don't know whether a smaller power of this polynomial also becomes identity. Thus, the order of this is less than or equal to 3. So the order of every element is less than or equal to 3. There is no possibility of having an element whose order is 27, and that is why G is not cyclic. Since G has no element of order 27, it's not cyclic. So now the solution is complete. Exercise 83. Let A and B belong to some group. A and B belong to some group. So A and B are group elements. What type of group, that is not given. Suppose that the order of A is M, the order of B is N, and M and N are relatively prime. If A to the power k equals B to the power k for some integer k, prove that Mn divides k. So B are given to group elements whose orders are M and N respectively, and it is given that M and N are relatively prime, that is their greatest common divisor is 1. Additionally, it's given that their kth powers are equal for some integer k. Then we have to prove that Mn divides k. It's not very difficult to find a solution, but in fact the solution is actually given in the text, in the answers section. So I am not going to repeat that here. What I want you to do is that you go to the answers, check the solution out and see if you understand the arguments given by the author. If you find something difficult to understand, let me know. Next, '84. For every integer n greater than 2, prove that the group un square minus 1 is not cyclic. Recall what the group un square minus 1 means, what it was. It consists of those positive integers that are less than n square minus 1 and relatively prime to it. and the operation is multiplication modulo n square minus 1. Okay, for example, not u n square minus 1, in general I am saying u say 4, the elements in u4 are the positive integers less than 4 and relatively prime to 4. 1 is there, 2 is less than 4 but 2 is not relatively prime to 4, so 2 won't be there, 3 is there, and here the operation is multiplication modulo 4. For example, if you take the product of these two elements 3 and 3 itself, then what do you get? 3 square is 9, but modulo 4, actually we have to find the answer modulo 4, so I should ideally write this. And this is 1 because 4 times 2 plus 1 is 9, so when we divide 9 by 4 the remainder is 1, and that is the answer. So in this group 3 square is 1, like that, u n square minus 1. Now it is given that n is some integer greater than 4, we have to somehow conclude that this group is not cyclic. And here we will take the help of the results that we have seen in the section on cyclic groups. One such result is this. Theorem 4.4. Let us recall the statement of this. If d is a positive integer, in fact, okay, a positive integer of course, but a positive divisor of n, then the number of elements of order d in a cyclic group of order n is phi of d. We have this result in the text. N is itself is also a positive integer and d is a positive divisor of n. Then the number of elements in any cyclic group of order n order d, that is those elements which have order d, their number in any cyclic group of order n is phi of d, but this phi is Euler's phi function. Now we write the solution. It is by contradiction. Suppose this is cyclic. Okay. Note that the order of this group is this. Now Euler's phi function value of n square minus 1, because that's what the group is. No, it has all those positive integers less than this number and relatively prime to it, and Euler's phi function calculates just that number. So the order is this. Now here I am going to use one fact from number theory. It's not very difficult to establish, but still you see, since n is greater than 2, we have n square minus 1 is greater than 2 square minus 1, which is 3, and that is again greater than 2. Thus 2 divides phi of n square minus 1. That is, there is a result which says that if you have an integer that is greater than 2, then the phi value of that integer is always even. Okay. And for this result, you can look from some other source also, but I prefer this one. See Theorem 7.4 of Elementary Number Theory by David M. Burton. Okay, so now see, we are now in a position to use this theorem. How? Because our group, you see, we have supposed that this group is a cyclic group and its order is this phi number, which can be considered here in place of n, a cyclic group of order n. And here we have a positive divisor d of n, that d here is 2. So that means according to this theorem, the number of elements of order 2 in this group should be phi of 2, which equals 1. So by Theorem 4.4, it has phi of 2 equal to 1 element element of order 2. That means there is only one element of order 2 in this group. We will now show that we can in fact find two different elements of order 2, so that would give us a contradiction. And one of those two elements is this. Note that n square minus 2 as well as 2 belong to this. Keep in mind that they should belong to the group, that is, they should be positive integers less than n square minus 1 and relatively prime to n square minus 1. Okay, let's see that for a moment. 2 of course is a positive integer. Is this a positive integer? Yes, it is, because since n is greater than 2, the smallest value of n is 3. Even in that case, we have 3 square is 9, 9 minus 2 is a positive integer. So these are positive integers and clearly they are both less than n square minus 1. This of course is less than n square minus 1. This is less than n square minus 1 because n is greater than 2 again. And the smallest value of n is what? 3, in which case we have 3 square, 9 minus 1 is 8, so 2 is definitely less than 8. So these elements are there in this group. Oh, but there is one more condition. No, they must be relatively prime to this. Since 2 itself is a prime, 2 would be relatively prime to this if and only if 2 does not divide this. Okay. Now, for that to happen, 2 does not divide this. N square minus 1. Is that true? Let me just see. No, that is not necessarily true, because if n is odd, then n square is also odd and n square minus 1 is even. So in that case 2 will not belong to this group, because 2 is not the element that we are seeking. Okay, what happens if I write n in place of 2? Let me see. Is this true? That we first have to see. You see, because n is greater than 2, n is of course a positive integer. And whether this is true, this will definitely be true. This is equivalent to this, and the smallest value of n is 3. In that case also this integer is greater than 1. 3 square is 9, 9 minus 3 is 6. So yes, so n just like this one is a positive integer less than n square minus 1. Now is n relatively prime to this? Yeah, n will be relatively prime to this. You see, if you consider a positive divisor d of both n and n square minus 1, then d would also divide this, and this is equal to 1. So d must be equal to 1. Similarly, you can prove that n square minus 2 and n square minus 1 are also relatively prime. So these two integers actually are in this group. Now next we calculate their orders. Note that n square minus 2 is not equal to 1. Just like that, n is also not equal to 1. These are all greater than 1. And 1, if you recall, is the identity element of this group. But what is this? Oh, and in this calculation where we are calculating the second power of n square minus 2, you should keep in mind that this product n square minus 2 times n square minus 2 is actually the product we have in this group, not ordinary multiplication. Okay, so this is multiplication modulo n square minus 1, and because of that we can in fact simplify the thing even before expanding the square or anything like that, since n square minus 2 can be written like this, and in this group n square minus 1 is equal to 0. So we have this. Keep in mind that in this calculation we are using properties of that operation, multiplication modulo n square minus 1. Ordinarily, if we are just simply calculating like this in the system of real numbers, then this is everything is wrong here. But in this group it makes sense. And what about n square? We are calculating the second power of n also. Since n square is equal to n square minus 1 plus 1, so this is also equal to 1. So we see that these two things, these two group elements themselves are not equal to the identity, but their squares are equal to the identity. So both of them are of order 2. Hence this is 2, and the order of n is also equal to 2. But we have concluded here that the group has only one element of order 2. So by what? We concluded above. These two elements actually should be equal in this group. But equality in this group means what? It means that n square minus 2 is strictly speaking congruent to n modulo n square minus 1. Or which really means this: n square minus 1 divides this difference. Now n square minus 1 is definitely greater than 1. It's in fact greater than 2 actually. And n square minus 2 minus n, it can be written as n square minus 1. Oh, but then we have minus n. Or in fact, we can we can simplify the things here itself. N square minus 1 is available here. So this divisibility relation implies that n square minus 1 has to divide minus 1 minus n. So we can continue this a little more. minus 1 minus n. However, this is not possible because since n square minus 1 is greater than 1 plus n. It's say dividing this also means dividing its negative from properties of ordinary divisibility of in the ring of integers. So n square minus 1 has to divide 1 plus n. Actually we could have continued this a little bit more and written this, that n square minus 1 divides 1 plus n. However, n square minus 1 and 1 plus n are both positive integers, and n square minus 1 is greater than 1 plus n, so it cannot actually divide 1 plus n. So that is why our first this supposition is wrong, because that is the source of this whole contradiction. Everything else we did is logical, but under this faulty supposition, so that must be wrong. So I need ink. Give me a moment. Supposition is wrong, that is this cannot be cyclic. So the only possible gap, not actual gap, but a gap for you may be that fact that phi of n is even when n is greater than 2. So you look for this fact in any good number theory book, or if you think of it for some time, you play around with some values of n, you will eventually figure out why it becomes even. And speaking of this Euler's phi function, the next one is just that, next exercise. Just that means it involves Euler's phi function. So this is 85. Prove that for any prime P and positive integer n the phi value of the number p to the power n is p to the power n minus p to the power n minus 1. The solution in its entirety is not given in the answers section, but a very useful hint is given. In fact, actually it's entirely given how one has to write the solution and what is the main idea behind this solution or behind the proof of this fact, that is given. Okay, so here also you see the answers. It will be a good practice for you to actually come up with a solution on your own. That is how to write the solution, since the ideas are already there. So you try to supply the logical solution the way a solution has to be written. If you don't get it, of course, let me know. The next exercise 86. Give an example in this respect. This in terms of having such a section named answers, this Gallian's book is a little unusual, because at this level usually books don't have any answers. Answers are not provided. Maybe some instructors, some lecturers get solution manuals, but we don't usually get them. We are supposed to struggle through the solutions and come up with whatever we can. However, sometimes it's nice to have a guide like this to some of the solutions, not all. So in that respect, this book is a little unusual. So now give an example of an infinite group that has exactly two elements of order 4. In Theorem 4.4, we calculate the number of elements in a cyclic group of order n, number of elements of order d, but that is a finite group. In this case, the theorem has no use. We have to produce an infinite group in which there are exactly two elements, that too of order 4. It may happen, and it happens quite frequently, that in this type of exercises where you are asked to give an example to show that something is true or to show that something is not true, it may happen that you never come up with the solution. However, when you find the solution somewhere, you see that, oh, this is so easy. Don't be discouraged if this happens, because you see, sometimes the ideas don't come to us. It's most often that we are not able to solve a problem and we struggle through a problem. We struggle through the solution. We may sometimes get partial solutions, not the entire solution. But whatever we achieve, we should be happy with that. It's not always the main goal to, of course, you should try to find the entire solution, but that's not the whole thing. if you don't get the solution, but in the process of finding the solution you learn many things, that is also okay, and that is good. In fact, some very complicated exercises are given in good books like this, not for the reader to actually come up with a solution, but to struggle with it, and in that process learn something. That's why the authors sometimes throw in some exercises that are either exceedingly difficult, even after having all the tools of the section where the exercise occurs, or it may need something that is found only far ahead in the book. Okay, so that's only for the purpose of struggling. Consider the set G of those complex numbers which have absolute value 1. Okay, let us consider that set. Note that for any two complex numbers in G, we have their absolute value is equal to 1 and so the absolute value of the product, which we know from elementary properties of absolute values, is equal to the product of the absolute values, that is also equal to 1. Hence, G is closed under multiplication of complex numbers. That's one thing. So we are in fact showing that this G is a group under multiplication of complex numbers. Is known to be an associative operation. Okay. The complex number 1 belongs to G, and finally if Z is a complex number in G, then in particular Z is non-zero, because Z has unit modulus, so it cannot be equal to 0. Hence, its reciprocal exists in the field of complex numbers, and the absolute value of that reciprocal is also 1. Thus under multiplication of complex numbers. So this is our group where we will show that there are exactly 2 elements of order 4. Now we know that the equation z to the power 4 equal to 1 has the following solutions in the field of complex numbers: -1, 1, minus I and I, where I is of course your complex imaginary unit, square root of -1. Note that these numbers actually belong to G, because the absolute values of each one of them is equal to 1. Also, -1 square is 1, but the square of this is -1 and not equal to 1. Hence, so we see that if we are in a search for the elements in G that have order 4, naturally that draws us to this equation. We want complex numbers set in G which satisfy this equation, and then something else also. So the available complex numbers are these 4. However, among them -1 and 1 are not of order 4, because smaller powers equal the identity 1. 1 of course is the identity itself, so its order is 1, and -1 has order 2 because of this equation. However, plus I and minus I, they don't have order 2, and also clearly they don't have order 1 because none of them is equal to the identity. So their orders must be equal to 4, and they are the only elements of that order. Hence, and are the So this is one example of an, and the group is also infinite. We know that there are infinitely many complex numbers whose absolute values are equal to 1. In fact, you also know from your study of, I won't say complex analysis, but complex numbers themselves, the structure of those numbers that have absolute value 1, those complex numbers, and they look like, let me just wipe this part off and then I will write. These are precisely those numbers. Where theta is any real number. That's how the complex numbers of absolute value 1 look like. And sometimes this thing is also denoted by this symbol. It's the definition of this symbol is defined to be equal to this. Okay, so this completes the solution and it also completes this set of exercises. So in the next Gallian video, we will start something new on group theory, and I will also go back to ring theory, although I will not do that polynomial part, because you need the polynomial part, of course, but I told you to go through that part from the Herstein videos. If you need something specific, you can of course approach me, but since you only you need that, you know who are you, okay? I am talking about this account. If you need something specific, you contact me through mail or by writing in the comment section. I will personally provide you that thing. And we will go back to ring theory, and what I have decided is, from now on Saturdays we will alternate between Gallian uploads and Lee's algebra upload. So next Saturday there will be a Gallian upload, and in that upload there will be 2 videos, one on group theory and one on ring theory from Gallian. And the Saturday after that we will have our algebra by Gregory T. Lee exercises from that. What this will do, this will shorten our cycle, where we have things like we go like this. No, first we have groups from Herstein, and then we see fields from Herstein's algebra, then we see vector spaces, and then in that cycle Gallian comes. So that now goes to the Saturdays. So after vector spaces we will then have calculus, then number theory, then graph theory, and it goes like that. Whereas on Saturdays we will alternately have Gallian and Gregory T. Lee's algebra. In Sunday is fixed. Sundays are for analysis, task analysis. So with this I end this video. There will be another one today itself, that is Lee's algebra. Yeah, I was supposed to do this yesterday itself, but I was not feeling really well. So that will be all. If you want to say something about these things, you can write in the comment section below, or you can mail me. So that's just it for tonight in this video. So see you in the next video. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.